a moment for me. I guess I'm still hearing the background noise. If all of you can mute, that would be great.
Yes, all are in mute. Let me mute my.
Okay, okay, perfect. Let me share my screen so that I can share the presentation. Is my screen visible? Just do let me know.
Yes, sir.
Yes, Sagar. Yes, sir.
Yes, sir.
Okay, thank you. Good afternoon, everyone. As Sir welcome me, I am honored to be part of all of you and share my industrial experience as well as my industry knowledge to you guys in this session. Myself, Sagar, I am a lead member technical staff at Mentor Graphics. Working on cutting edge technologies which are part of the industry like DDR, PCI, AXI, HB, what sir introduced me. So I'll talk about what are the methods and the areas which we focus on, and what is the gap which is there right now. Say for example, if somebody has a knowledge of RTL or a verification and they want to be in design verification join your, like they want to join industry as a design verification engineer, then what should they know, and what as a faculty or what as a teaching faculties we should provide to students, so the industry bridge gap between the college and the industry should be fulfilled. So that's my idea in today's session. I want to touch base on the methodology which is being used in the industry and widely adopted across the entire industry on the design verification side, so that if we can impart the same to the students, that would be very helpful to them. I personally, when I started my career, I had to go to Bangalore and learn those technologies from the training institute, which charges hefty amount. So it would be an honor for all of us if we can impart all the learnings which we are doing from last 3-4 days, as I know, to the students, so that they can use these techniques and these languages so that they are ready for the industry directly after the college. So that's my plan for today, and that would be my agenda. So this is me. I would not be able to share my video because my camera doesn't work. This is me for just for everyone's sake. Okay, so what I am going to discuss today is I would mostly focus on. Okay, let me see if I can have the pointer option. Yep. So I would mostly focus on the SV side, that is the system Verilog side. But before that, I would just start with the flow and why we need a design and verification. What are the various methodology used in industry? Then I would jump into the system Verilog side. I would give an example, and then I would introduce to a UEM, which is obviously an extensible of the SV. So, and then what is obviously the future of the design and verification. Please feel free to raise your hand and ask any questions if you have any time during this interaction. Okay. So this is, I guess, from last 3 days what you guys are going through. So you know all of this. So what my main area is, so you have an RTL or design spec in the Verilog, and then you need to verify that, and that is called as pre-silicon verification. And that is what my role is right now. So currently I work at this area, and my idea is, like, what we do is we create a test bench to verify this design at the pre-silicon level only. So my job starts as soon as the architecture and the design is ready, and that's where we start creating an architecture for the test bench, and we create a kind of an test bench so that we can verify the functionality of the RTL. So whatever is there in the spec, it is written in the RTL. It has to be first verified with the pre-silicon verification methods, and then it has to be converted to the synthesis. Sorry, any questions?
No, Sagar, you continue.
Okay, if I heard a background noise, so that's okay. Thank you. Okay, so after once you are done with the pre-silicon verification flow, then you convert into the synthesis equivalence check, PNR or STA or whatever. So I guess all those sessions has been done recently, but I would talk about this area. Okay. So why pre-silicon verification is needed? What is the role and what is the major significance of a verification of a design? So you have to check the functionality of the DUT RTL as per the specification. So a design RTL writer would be a different, and a verification test bench writer would be a different. So say for example, if RTL guy has written something understanding the spec, it is not that he might have understand the spec correctly. So as a test bench writer, the job is to create a test bench in such a way that we find as many as bugs possible in the pre-silicon level only before it goes to the synthesis and post-silicon stuff. Because if bugs are identified in the design early, it is very good. But if not, then that can be expensive. Believe me, like we have to go through, or the backend team, the synthesis team has to go through a lot of pain, and it costs $1 million of to company, and that's why the most number of jobs in the entire VLSI industry is in the verification, pre-silicon verification, because you want to catch the as many as bugs possible at as soon as the RTL is ready in the pre-silicon side, and not after your chip is out and then you again have to respin it. So obviously there are other different kind of bugs when you go on the backend side, but you want to find as many as bugs possible as before the chip is even going to the synthesis level. So that is the major requirement in the industry, that why pre-silicon verification is needed. And currently, if I know correctly, for every one RTL engineer, there are 10 verification engineers there present in the industry, so that they can find the bugs, because bugs can be anywhere in the design, and you need to check each and everything in the design before closing it out so that it can go to synthesis. Okay. So currently in industry, RTL or the design under test is mostly written in VLDL and Verilog. Okay, that when it comes to test bench, the functional verification part of that is done in either SystemVerilog, or UAM, or at C code. When you go to the SOC level, there are some test cases written in the C side also, C or C++ side also. So what could be the basic test bench structure is, you generate the stimulus to the design, and you check the results, that whether what I intended has come out or not, is it expected or not, and then you measure the coverage, that whether all my functionality has been covered or not. So this is what the current industry do actually. Like they generate a constraint random stimulus. I'll talk about constraint random stimulus in the upcoming slides. Then they pass that stimulus to the DUT. Then you check whether whatever I wanted or whatever I was expecting, the results are correct or not. Is my DUT behaving correct or not? So there are obviously checkers on that, because of checking whether your DUT works or not. And then there are functional coverage. So functional coverage is an aspect where view covers all the functional metrics of the design, and you say that okay, now I'm done with my verification. Now you can go to the synthesis or any other flow, whatever you want. So that's how generally the test bench are developed right now. This is just a basic an overview which I wanted to give before I proceed to the system verilog. So what I'm going to do now is I am going to explain the most necessary thing, that is called a system verilog, because test bench currently are written in SV or UM across all the customers in the industry. Like if you name any Qualcomm, Intel, Nvidia, Broadcom, what are the big design companies you may, even in Mentor Graphics, at other customers. So we write and we code everything in system verilog and UM for IP SoC or subsystem level. So what and why system Verilog? Because a lot of people are familiar with Verilog already, right? You know that okay, I can write a test bench in Verilog. but Verilog has a lot of limitations which SystemVerilog overcomes. The first is you can do and constraint randomize. Okay, there is no way in Verilog you can do randomization. Even if you can do, I know there are ways you can do, but it doesn't allow you to constrain it and give a proper randomization of you. There are OOPS support like class-based entire test bench. Currently in Verilog, if you write a test bench, it would be within module, and it is called a static test bench. While the test bench in SystemVerilog would be purely based on the OOPS. Those who know C and C++, most likely C++ or Java, they would be very happy with this today's session, because SystemVerilog is mostly based on C++, or that is called as object-oriented programming language concept. So that is what I'm going to target about, like just explaining you the basic stuff of OOPS or C++, so that once you go to write a test bench in a SystemVerilog, you know that okay, these are the basic concept which is there already in the SystemVerilog. Okay, then there are new data types like logic in the SystemVerilog. You can write an assertions, coverage, C model integration with the help of SystemVerilog. So that is not possible with Verilog straight away. So that's why it narrows down the gap between design and verification engineers. So that is why this SystemVerilog is very, very important for current use. Any questions till here? Okay, let me go. So now I will fully focus on SystemVerilog and the OOPS concept, because this is the fundamental and the basic building block of a SystemVerilog test bench writing. So object-oriented programming in SystemVerilog. Uh, any questions? If you can please mute your mic, that would be great. Koringa sir, if you can mute the mic, I guess, for the speaker. Thank you. Yeah. Okay. So OP in SystemVerilog is supported through class data type. So you have to write a class, and in that there will be a lot of encapsulation. What do you mean by encapsulation? Like a class would have a data type, members, and the properties of the class. You will have a task, function, and the different properties within the class encapsulated. Obviously, there is an inheritance concept, like you can extend the class and use the extending class from the parent class or the base class. Then there will be a data hiding concept present, like you can embed a lot of code within a class and hide it, like make it a public, local, uh, and raise your abstraction level as well. And then there is a polymorphism, parameterization, which I'm going to talk about in the upcoming slides. So why classes? Why SystemVerilog chooses classes? So that it can be used to model a reusable verification environment. Because currently with Verilog, there are a lot of limitation when you want to code a complex test bench. Sorry if I'm still hearing the background noise. If people are not on mute, can please mute them. Uh, Thank you. Thank you. Please mute yourself again, like if you are not on mute. So why classes again? So classes can be reused easily, and you can create a complex verification environments very easily using the class-based methodology rather than the module and module which is there in the Verilog stuff. So that it allows also to raise your abstraction level, and which you can easily operate from outside world also. Okay, so that is why SV and OP entire concepts are there, and with these concepts you can easily create the reusable verification environment. So that's why industry has adopted this standard, and this is IEEE approved standard. So people, anyone can use it, and everybody, it will be accepted everywhere across the entire globe. Okay, so let me explain you what is the class terminology. So class is nothing but it defines a type of data and methods. Like you would have a members inside that, a properties inside that, and methods inside that. So class type are constructed dynamically. It is not present at a static time. Well, like when you compile, it would not be present. When you create it, then and then those types would be there. And class objects are accessed via class handles. So I would anyways talk about that. Okay. So what is class? As I said, like it is a data type, right? This packet is a data type unless and until it is created. So class variable referred to as a class property. So this status, this data are your properties, while the get status is a method, and all the members and the methods, or it can be a function, so it can be a task. They are called as a member of class. Okay. So class declaration does not allocate any memory. So if you just write this piece of code and just compile it, it does not create any memory. You need to create a new to get the memory of that. So what is new, like how you instantiate that class? So via a new constructor. So this new constructor is inbuilt for all the classes. Okay. So say for example, you written a class in SV, and you do a new, you take an handle, this my packet is an handle of this class, and you do a new, now you have an entire memory to you. So now you, this my packet dot command, my packet dot status, my packet dot data can be accessed. Before doing new, you cannot access any members of the class. Am I clear here? Any questions?
Yes, participant, if you have any questions, you can ask by unmute yourself. Wherever you will find any questions in any slide, you can directly ask. So at that time, it can be solved.
Okay. Thank you, sir.
Yeah, continue.
Sure. So,
If
okay.
any questions in a chat box, I will interrupt you. Okay. So
Sure,
you
sure.
can.
Please. Yeah, sure. Okay, let me hide this if yeah. Okay, so now say for example, you want to pass an argument to any variable. Like here you can see I'm passing status. I want to pass a 5 from the constructor. You can do that also. So SystemVerilog allows you to pass an argument from a constructor class also. So that this is used in multiple ways also. I'm not going to go in detail. These are just the basics which I want to touch before showing you to the actual example of how you write a test bench using this methodology of to verify your RTL, which is written in the Verilog. Okay, so what are the properties? As I had mentioned, the command, the status, these are the properties. Okay, and properties can be of any type, like it can be int, bit, byte, logic, of any time. And similarly, like class properties have a dynamic lifetime. Okay, and class properties, the most important thing is are referenced using the object. So as you see here, I have taken an handle. I'm now creating that handle. So now the memory is assigned, and now I can access those members using that particular object. So packet h dot command equal to ideal. I can assign that. I cannot do directly command ideal. You have to access via the handle. Okay. So that is the basic fundamental of any OOP language. Okay, for similarly, if you, this is my function, set command was my function, if you recollect from the previous slide. So this is my function, and this is my function. So task set command, here is my task. Okay, and I want to access that. So how you access it? Again, you have to do packet h equal to new, and you do a set command. You can use using that. As with Verilog, task can block and consume time. Like functions would be cannot consume any time. Like function has to be run within a 0 time. So that remains the same. Who knows Verilog? So that is the same functionality even used by the system Verilog. Okay. Okay. Now this is very interesting. How you copy an handle or how you copy an object. Okay, so now I have two handles of packet class. This is my class packet. Okay, now as you know here, I'm creating the first handle, packet1 handle. Okay, I'm doing a new. Now I can assign that handle to another handle using just an equal operator. Okay, and once I assign that, only the handles are assigned. Packet1 has a memory, and packet2 will be pointing to the same memory location of packet1. Okay, so when I do packet1 handle dot status equal to 5, and when you display it, so this is a dollar display, how with which you can display the values in Verilog and SystemVerilog. When you display a handle status of the packet2, it would be 5 only, because it's just an handle assignment. But when you create in such a, in this way, like this way, this is called a seller copy also. When you do a packet2 equal to new and assign the values of packet1, then you are creating a different memory for packet2 as well as packet1 also, right? So packet2 dot status, when I do, it will be 10, and when I and the value, if you print this one, it would be 10, like for the packet2. But now when I do a packet1 handle dot status, the value would be 5, because that has not been changed. You are just changing the status value which is there inside this object and not this object, because now after this statement there are two different objects having different memories. Here there was only one memory location. Any questions there? Okay, sounds
No.
like either people are not understanding or they are still sleeping. Yeah. Or like they are understanding everything. Okay. 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 So now let me explain you a bit more about the extending class, how you can extend the class, which is a very good feature there in the OOP language. Okay, and it has a lot of advantage of using the extended class. So original class, my packet class is called right now is the base or the super class, or some people call is it a parent class. Those who work on the Java or C++ side. Extended class is the derived class or subclass. So my error packet here is a derived class or a subclass. Okay, so this is my base class and this is my derived class. Okay. So as you can see, so now class error packet would be similar. It would have the feature or the properties of packet parent, command, status, data, and it would have the additional property of itself, like that is an error. So the what I am showing here is, when you extend any class, it inherits all the property from the base class. So it is inheriting all the properties of the base class. Okay, like command, status, data. And so this error packet would have, although you are just writing one statement, but it inherits all these three statements automatically. Okay, so that is one of the very good functionality even SystemVerilog provides. I'm so why I'm showing all this is I'm just building blocks of I'm just explaining you the building blocks of SV, which again, which will be very useful when I will take you and run through the original example of how people write the test bench in industry level. Okay, when you want to construct an extended class, okay, so now this is my parent class or a base class, and this is my derived class component, which is extended from this class. You have to do a super dot new while writing this class, because say for example somebody created this class only, like directly I say component, I take an object handle of this and I do a new on that. If I don't write this statement, this class would never be created and then it would give an error. So either you create both the class separately, like you take an instance of this class and handle of this class as well, or if you just create this class, super functionality allows you to create the base class also. So that indeed is again a very good functionality which SystemVerilog has. So you can use that while directly constructing the extended class. Okay, and you can again similarly, if you are passing any argument in the function you have to pass the argument similarly to match it in the super dot new as well when you extend it. Okay. Okay. Okay, so now so what is inheritance? Like, let me explain you more in the detail. So this is my base class again. I have some members or properties. I have a function, and now this is my derived class. Okay, which is extending from the packet class only. It has a the additional functionality like it has a bit error, show error, and set status are same in both the class. If you see here, they are both are same here, but both have a different functionality because I can create an object of this class and do a object dot set status, or I can create an object of this class and I can do an object on this stuff. Here the only change is the codes are different. Like if you see the functionality within that, status equal to a, while here you are doing status equal to a plus. Now let's see what are the different combinations you can try with the inheritance, and how inheritance is very helpful. uh, uh, you take an instance of packet class, that is packet underscore h. You can take an error packet instance similar, and now you are only creating error packet equal to new. Remember that we have not done here function new and super dot new. I'm just doing only creating this class error packet. I have not created this class. Okay, so as of now I can only access the property of this derived class error packet dot command dot error dot set status, etc. But when you do packet handle equal to e packet handle, then even packet handle can now access those properties. Okay, but can you show now I'm doing packet handle equal to e packet handle. Can I do e packet handle equal to packet handle as shown here? No. Why? Because packet is a base class. It cannot have the properties of the child class. Okay, child can have the property of the parent, but parent cannot have the property of child, right? So that is the reason you cannot do child equal to parent. So as you can see in the child and parent relationship, this is my child, e packet is my child, and p packet is my parent. So c equal to p, that is child equal to parent, not allowed. But packet equal to child or parent equal to child is allowed, because child has the property of the parent, but parent cannot have the properties of the child. So that is the main reason, and this is very important while you write a test bench. You cannot do certain things, and this is one of them. So this explains the entire concepts of the inheritance, one of them. Okay. Okay, so let me explain you in even much more detail about how you can take the advantage of inheritance. As I mentioned in my previous slide, you cannot do C equal to P, that is child handle equal to packet handle. But say for example, even if you want to do that, because here you have already assigned a child handle object to a packet handle. Now you can say, somebody can say me that, okay, can I assign now this handle to another child handle, like can, because I have already have the memory, parent handle is already pointing to that. So these are just a pointer, right? Objects are nothing but a pointer. Now can I do packet handle equal to another child handle? You cannot, unless you do a dollar cast. So that's what I am doing, and that is called as dynamic casting. So as you see here, my parent class is A, and this is my F extends from A, and even my B extends from A. Now G and C extends from B. So as you can see, A is a property V. F, since F extends from A, it has now a property V and W. Okay, because it is an inheritance. Even B is extending from A, so it has now a property of A as well as property of itself, that is V and X. Now G, since G is extending from B, it has, and B is extending from A, it has a property of G, that is Y, B, that is X, and property of V. So that is how the kind of you can say the hierarchical reference of the class can be done. Okay, and this is the perfect example of a inheritance. Like, okay, so upcasting is always legal via direct assignment. What do you mean by upcasting? That is, I can do like A equal to B or A equal to F. That is always legal. Like I can assign F to A, I can assign B to A, I can assign even G to B, and which can be internally assigned B to A. So from this hierarchy is possible assignment, this hierarchy possible. But since A is the parent, you cannot assign saying, okay, F equal to A or F equal to B. Like you cannot assign a parent handle to a child handle like that. Okay, but you can assign a child handle to a parent handle as shown in the diagram. Like I am showing the entire path. I can assign G to B, B will be assigned to A, but I cannot do like reverse. So for that, say for example, you want to assign C to A, you require a dollar cast stuff, or even G to A, you require a dollar casting stuff. So to give even more example, I wrote it in a parent and child form. So there are two functions similarly in both the child and parent, that is function display, and I am printing address in one and I am printing data in one. Okay, so this is my parent class, this is my child class. Now when I first have to create that, right? So I'm just creating, I'm just instantiating, I'm not creating the parent object, remember that. I'm creating the child object C equal to new, so the memory for this child class would be allocated. Okay, I'm taking another instance of child class. I can take as many as possible. SystemVerilog does not have any limit on that. Now with the created one, I can now access the property, okay, of the parent as well as the child, because c dot address, that is this guy, and c dot data can be accessed. Now I am doing p equal to c, that is I am pointing my child to parent. So okay, but now the child p also would be pointing to child. So somebody can say, okay, now if I have a c1, can I do c1 equal to p? No, you cannot do unless you add in dollar cast. Okay, because this would allow and because of dollar cast, this would be checked at the runtime, like at the simulation time, and then you can use the advantage of c1 dot display. So without even creating c1, you can access the display method of the C1, the child one, using the dollar cast via a parent property, via parent handle. So that is called as a dynamic casting of a class. Okay, so this is also one of the important feature of a system Verilog. Any questions here? Because I expect some questions at least here.
No any question in chat box.
Okay, so either people are sleeping or they are not able to get, or they are not interested. Okay, no
They
issue.
all are from same field, so they are interested and they are learning. Might be they know.
Okay, okay, that is perfect
Or
then.
they, they got everything.
Okay, yeah, yeah, that is perfect. Okay, so let me go to the next concept called as polymorphism. So what is polymorphism? In a layman term, in a common man term, it is like say for example, we all have eyes, right? Even I am viewing it and you are viewing it, but I am viewing it differently and you are viewing it differently, but eye is a common. Or you can say there is a car, but somebody can have an Audi or somebody can have a Maruti. So but a car is same, right? It has a four tires, the basic property is same, so that is called as polymorphism. It has an the same code can act differently for different types. Okay, a key requirement for any OOP language. uh, if you write a parameterized class, you can say that that is also a kind of a polymorphism. And to achieve polymorphism at the runtime, you can use an example of virtual class method, which I'm going to show here, because most of the industry standard base use this advantage, which is very helpful for them while writing or creating a test bench. Okay, so there are as I mentioned here, there are two types of polymorphism. One is static polymorphism and another is dynamic polymorphism. And static polymorphism can be achieved using parameterized class, and while dynamic polymorphism can be achieved using a virtual class methods, that is either a task can be virtual or a function can be virtual. So that is what I'm going to show here. Uh, okay, so the override function, when I have a virtual method which is there inside my packet or my parent class, set status here, you need to declare it as a virtual. Okay, and when the class is extended, sorry,
Excuse me, sir. Excuse me, sir. May I interrupt you?
I didn't get
Shall I
your question.
interrupt, sir? Shall I interrupt, sir?
Yes,
Hello?
if you have any questions, yes.
Sir, actually, there one slide you told that any OOP language it is mandatory to learn this SystemVerilog. So, up to what level, I want to know to what level we need to learn that any C++ or any other Java like languages so that we can cope with this SystemVerilog and UVM. Because
So
in our college, normally we just up to the Verilog.
correct.
They are not teaching this EVM or this SystemVerilog. That's why I think the understanding level now that is not much, so that you can understand. So
I got
I want to know.
I got your point. So even I don't know C++ to be honest. I learned directly system Verilog. So whatever I'm imparting the knowledge here, right? If you even learn this, this is enough for you to start system Verilog. Okay. After this lecture, I'm pretty much sure if you understand and focus on this, you would be able to write a test bench in a system Verilog. So
Normally,
you
sir, yes, in a student point of view, I also wanted to know that yeah, is it mandatory to take any extra training related to this VLSI to enter this any good and VLSI company? Because in our college normally we teach up to Verilog. So
correct.
please
So
check.
the yes, so industry uses the system Verilog and UM for writing the test bench, and now also even RTL are starting to getting written in the system Verilog. Okay, because system Verilog is a synthesizable code. Okay, so you can write RTL in system Verilog also. What you can do is once you can go through the slides which I am going to there, you can start learning system Verilog from there are a lot of multiple open forums, and you can start learning from there, and you should be able to learn that easily, and then you can apply. There is no way, there is no mandatory rule that okay you should go and train yourself. Even you know the basics of system Verilog, a company will hire you. That was what my understanding is, because even we take interviews, and if I know people who understand these simple concepts, we will hire you. Any other questions? Okay, I guess if there are no questions you can mute. Yeah.
If you'll join a VLSI company, you have to work very low package for 5 to 6 years. Then only you will get some decent amount. That's why now maximum students are teaching for software companies. So is it a myth or fact? I want to know that one, so that we will encourage students to this field.
uh, it's a myth, I would say, that VLSI company doesn't give a good package. Yesterday Mansi Masrani also gave one of the lectures. She is also at a very high package. Even what I am giving, we all are at a very good package in the company. And to be honest, we are paid as equivalent as to the software fields like what Amazon, Facebook, Google pays to the software guys. Okay, because the demand for knowing the VLSI, like knowing this verification or physical design or synthesis, is very much, and people or the number of engineers who knows this in and out are very less. So obviously when there is huge demand and the supply is less, people are going to pay it high. Okay, so it's always a demand and supply stuff. So if currently in the industry there is a huge demand of VLSI engineers and the supply is very less coming from the colleges. Any other questions?
No, thank you, sir.
Okay.
One comment in a chat box, it's going too hard.
uh, what is going too hard, like the concepts are going too hard?
Yeah. So
Okay.
I have to ask to participant, Mr. Saurabh, you want to Any comment in this, Mr. Saurav? Okay, continue, Sagar.
Sure. Okay, so what I was explaining is if you have a virtual function in this class, that is a packet class, and if you have a similar virtual function in the child class, that is an extended class, and if the prototypes are same, using the parent handle, like using this, and if you do a status, what would be the value? Would it be 5 because I'm passing the value 5 here, or would it be 6? To explain you further, I created a small example so that it can be explained properly. So say for example, this is my parent class and this is my extended class. Okay. Here my task is virtual. Okay. And I have a display, two display, like this is class A, this is class extended class A. Now I am creating a handle of my parent class A, that is A, my A, and now I am displaying. So what would be the answer here? Like what would be the result of my a.disp? If anybody is awake and can answer me. No. Okay, that means nobody has got this, because it's very simple. I'm creating the object of this class and I'm just doing a disp, that is I'm just calling this task. So what should be the result of this? Like what output the simulator would give?
This is class A.
Yes, perfect. Thank you. Very good. Now, when I create a child and I do a new, and I assign my child class to a parent class, and if I do the same, like I have done my a.diff again, after doing this statement, like I am creating the child class and I am assigning that. If I do that, now the next time my print would be this is extended class A, because there is a virtual here. If it was not to be a virtual, again it would be this is class A. So the first time when I do a my a.disk, this is class A, and when I do a next time, this is extended class A. So with this way, you can achieve virtual polymorphism. The idea, if you see here, the property is same. Both are tasks and both have the same arguments. Like there are no arguments to pass to the task, but both the proper prototype is same for both the tasks. And so this is what it is called as virtual. So once a virtual, always virtual. I mean to say, if there is another class which is extended from A and it has also diff, it would be a part of the virtual method. Okay, so as many as class you can extend from this class A, and all those classes, if they have this diff, they are all part. You can achieve the polymorphism stuff. Okay. So now with the parent object, I can call the child's property or child's method, I should say, using a virtual stuff. Okay. Any questions here? Okay. Okay. So I did talk about you can achieve the static polymorphism using parameterized class. So SystemVerilog provides a beautiful way of passing up parameterized stuff, which with which you can create many different objects just by writing a single piece of code. And when you create an object, you can do multiple things here. So this is my type t by default is an int, say for example, and here I'm again passing another argument, that is int w, and this is my this hash sign is your parameterized sign. Okay. Now I have taken t items dollar, that is a q. This dollar represents a q here, so this is a q, and t is nothing but a int property. For example, you can say that, and these are various functions inside that. Now when you create it, when you create this class, and say for example, if you give a bit, then a t which is int by default would be replaced with a bit. Okay, so it is now a stack of 10-bit vectors. If you pass the parameterized while creating or while instantiating with a real, you have a stack of reals. You cannot directly do that because you have to pass some parameters, because type t is not given any value by default, while w is 5 because it is given default. You can change it, like you can do comma and say okay 10, then 10 value would be assigned to w. But what is the why I am showing this is, with this way you can do a multiple specialization. So same code can either work as an integer, either a bit type, a real type, or whatever. Okay, so this is a beauty of a parameterized class which you can use so that you can generate a reusable test bench. uh, any questions? I know it might be sound on a first go a little bit difficult, but this is a very simple concept. Once you understand the concept, this is very simple, because I'm, instead of Verilog, I'm just showing a class based test bench, nothing else. This is just a class functionality, and it is very simple. Like what I am showing is how you can access the class, and then how you can inheritance take the advantage of inheritance, and now I'm showing how you can take the advantage of polymorphism.
Sir?
Yes?
Sir, as you mentioned, reusable test bench.
Yes.
Is it similar? What's it like in Verilog and SystemVerilog? What's the difference between that?
So I explained in the first, like, so in Verilog, you write the test bench in the module and module, right? Because there is no class concept in the Verilog.
Yes, sir.
Right? Yes. With SystemVerilog, there is a class concept, and as I showed in the first slide, like why OOP is important for creating any reusable environment. Forget about the test bench, any reusable environment. Even software guys write everything inside a class base. If you know Java guys, whatever you know, like whatever the software guys, they write everything for creating the reusable architect. There is an app, I want to create an app, a software app. I would try to create something in a similar way which I can be reusing every time. Because now I have, say for example, you are using a mobile, and you have a processor inside thing. Do you think that the company who is generating mobile, as many as mobile in a year, like 5 to 10 mobiles, they would be writing code from the scratch every time? No, right? They have now created a legacy code, where you say for example, now you want to, instead of 64 GB, you want to extend to 128 GB. What you do? You just extend the class, you add one more feature saying that okay, now my memory has to increase to 128. Okay, so and you verify every entire your RTL, that my RTL, yeah, like your design works on this 128 GB also or not, your RTL works on 64 GB or not. So if a mobile comes in the variant of 64 and 128 GB, what they are doing internally, they are just extending the class. You can say in that. I'm giving very high level answer of what is the question and why class is very important. You cannot do that in a module. You cannot extend module. As simple as that. You have to write your entire code in a Verilog if you just want to change one functionality, right? Because there is no inheritance there is no polymorphism there, and there is no extension there. So that is why this is important, right? And that is why this is so popular across industry, that every design and verification engineer knows SystemVerilog in and out, and that is the priority, and that is why this is so advanced and so much in use, because you can do a lot of things but just by taking the advantage of this SystemVerilog concepts, like OP concept, which I mentioned. Did I answer your question?
Yes, sir. Thank you, sir.
Hello, sir.
Yes.
Sir, as you have said that you cannot extend the Verilog module, but parameterized modules are available.
Absolutely.
So is it helpful?
Yes, absolutely. Absolutely, it is helpful. So you can replace your parameterized module with the parameterized class, right?
Yeah. Okay.
Yep. So that is what I was trying to relate it. Like, so, but what is, even if the parameter modules are there, you have to instantiate it everywhere, and similarly in the class also you have to just instantiate. You can change it here, like instead of int, you can make it a bit, as I showed. Instead of that, you can take a real. But even say for example, you have parameterized module which would serve you polymorphism stuff. But how you would take the advantage of like extending the class? Say for example, I want to add some features. Now your module is free, right? If you want to add one feature, you again have to change everywhere. Like you have to add a parameter here. So say for example, I want to change 110 features. So would you keep on adding 10 features in a module? No, right? Instead of that, with the class, what it comes, you just extend that class and add 10 more features in that class, and you are done. Right? Does that answer your question?
Yes, sir.
Okay, perfect. Any other questions? Good to know that people are now awake. Okay. Okay. Uh, SystemVerilog provides even parallelism also. Like you can run multiple codes in parallel. Again, this is not there in the Verilog. So those who say that why Verilog and why not SystemVerilog, again a new feature for all of those saying that what are the advantages of SystemVerilog. So fork join is a concept of Java. Okay, but it is inherited in SystemVerilog because that is an oops concept. It is very simple. You can do achieve a parallelism here, like you can run multiple threads at the same time, and it will run differently concurrently, but differently and concurrently, I should say. So here, as I show in the example, I have a fork join in my initial begin end block. Okay, now I have three threads, that is b1, b2, and I don't have the name for this third thread. Okay, so what happens is or you can say a three, yeah, I have a name for that, a three third thread. So all of this thread within fork join start at the same time, as you say, start at the 0 time, as you see here. Okay, the first thread finished would be hash, since this is hash 1, so after 1 nanosecond or 1 time unit, you can say that okay, this would be finished. That is, my b2 would be the first one which would be finished. Now, again, these two are running concurrently. So after 2 units, that is after 2 time, you say B1 is completed, and after 3 times, this third is completed. And then after all of these are completed, then your simulator comes out and would print this one. That is a begin end at time 4 nanosecond. Okay, so and your program would be finished after 1 plus 5, that is 6 nanosecond. All of this, it is not like adding. Okay, it is not like that. Okay, this is first, like after 2, then 3, and then 3 6. So that is not happening. All of them have started concurrently, and that is why you are saying this is getting finished first. After that, this is getting finished second, and at time 2 only. It is not like that. Okay, first this is 1, and then 1 plus 2 3. No, at time 2 only, as you see here, it is getting finished, and this is getting at time 3. Okay, and then after 3 ns, it comes out at join, because all the three process are done. This statement would be printed, and that's what the output is shown here. Any question? Because what fork join does is it forks all the thread concurrently. That is the use. What is fork join is? It forks, it spawns, it throws all the threads concurrently at the same time. Okay, so now I will give you a real-time example why this is helpful. Okay, in an SoC, you would have an in a laptop, say for example, you would have an audio jack port, a USB, a CPUs, other peripheral device like I2C, blah blah blah. And now I want to start. As soon as you start the processor, as soon as you turn on your CPU, you start multiple threads at the same time. Okay, you start multiple threads at the same time. And how you do that parallelism within a language? With this help of kind of fork join, you start a USB, you start your graphics driver, you start your I2Cs or SPI devices, or your mouse, keyboard, whatever. So all those threads would be forked simultaneously and start concurrently. So that is where that is useful, which is not present in Verilog. Okay. Any questions? Because there are other two variants of fork join which I am going to explain, like, okay, so now there is something similar as fork join any. Okay, even fork join also starts at the same time, but what any does is, if any one of this thread is finished, it comes, the program or the simulator comes out of that block and start executing the other threads, while the other threads would be within the fork join would be running concurrently or in the background. Okay, so if you see here, my B2 is finished after 1, and then it comes out of this block, join any block. Then, as you say here, as you see, has 1. So at 2, this is getting printed like begin end, as well as this B1. So both are getting printed, as you see. At 1 nanosecond, my B2 is printed, and at 2 nanosecond, my B1 and begin and both are printed. So in the previous program, if you have seen, first all of these three has to be completed, and then the join, it comes out of the join block. While any is, what does any means? If any one of this thread is finished, it can come out of the this fork join any block. Okay. Any questions? I'm hearing some background noise. If you can mute yourself, that would be great. Yeah, thank you. Okay. Now there is a fork join none also, the other aspect of that. Okay. And again, please consider the real-time example which I gave on the first, like you have an CPU and you have the peripheral device connected to your computer. This is very useful of having a parallelism in your code. So this is kind of mimicking your entire design of the real time in your code itself only. Okay, so there is fork join none. So what does it does? Without completing any of the forks or without any of the threads in the fork join block, it directly comes out and start executing this also. So this happens at time one because it has come out since it shows it is none. It directly comes out and has displayed this begin end first, and obviously then it would do the rest as it was like previously, like this is displayed first, then this, and then this. But the idea is it need not need to wait for anything to finish, and it can in the background it can start executing the other processes also. So that is a beauty of fork join none. Okay, so you again in the real time example, if I say CPU, there are multiple threads, and if you use this fork join none, you need not wait to okay that all of them has to finish. Like if you use fork join, then all of them has to finish. Then and then I can do some other procedure. CPU can now with fork join none can fork this all the threads. Like it can initiate USB, it can initiate your graphics card, it can initiate your initialization to mouse, keyboard, and it can do other processes also, like talking with other peripheral device. So that is the beauty of fork join none. Okay. Okay, and now say for example, I would not go in detail because I was expecting some question here, but if you want to do a wait for fork, like if you even if you have done join none and if you want to wait fork to be completed, you can use the advantage of wait fork. Okay, so that is the utility. Still, it is a very good utility present in the SystemVerilog, which you can use it. So what does it do is it will allow for all the fork join to complete it, and then the next statement would be executed. That is after wait fork is achieved, you will see this this would be the last statement to get printed here. Okay. Okay. So now this might be interesting for a lot of people. So SystemVerilog. So as you can see, this is my DUT written or RTL written in Verilog, and this is my test bench which is written in SystemVerilog. Okay. Now I want to communicate between them. In the Verilog, what you do is you instantiate some of the signals, the duty signals within the test bench, and start connecting them. SystemVerilog provides a beautiful and a powerful feature called as interface, okay, which is not there in Verilog. You need to add interface keyword when writing those the interface so that it can connect your test bench to that, and you can do a lot of things here, like multiple things like synchronization, asynchronization, give the direction of the ports at the interface level. Okay, rather than creating something very messy in the Verilog, what we do, you can use the advantage of interface level. So it encapsulate the interconnection and communication between the blocks. So what exactly the interface has? It is similar to what you have as the module. Okay, you would have a group of signals, a bunch of signals, which is there in the module. You can pass that as input, output, whatever. It is similar to module, but it has other two unique features which is not there present within the Verilog or modules. That is a blocking block and the mod ports. I'll talk about that. Okay, an interface also can contain classes. You can write classes within that, and all obviously also initial and the always procedural or continuous assignment statements like assign or procedural statements also you can write within interface. Okay, I would now explain on clocking block and the mod ports. Okay, what are those? Like what is the need of those? So so now in Verilog, the issue here is with the Verilog is, say for example my RTL duty is working at 1 clock, and in you are writing or from test bench you are driving at the same clock, then there are high chances that there would be a race. So with clocking block concept, what we do with the test bench at the SV level is we try to separate where we drive and where we sample or where we monitor the signals. Okay. So say for example, if I drive my test bench signal after a clocking edge, so that it can be reflected at the next clocking edge. So if you see here, if I drive here, then it would be reflected at this POS clock. If my my RTL as well as my test bench is being driven on the POS of the clock, and with this way, there are high chances that you avoid a race. And similarly, you are sampling or you are monitoring your signal. Say for example, you want to sample any signal, you are sampling it just before this POS, so that if you you know that what would be the value of this at the POS. Okay. So that's where the input skew, that is your one which is being sampled before the clock, and there is output queue where after which you drive the signals from the test bench to the DUT. Okay, so this is very good and very unique feature in the SystemVerilog, with which you can drive and sample your signals easily. So those who know setup and hold time might relate the concepts here of how we avoid the race when we drive from test bench to DUT, because if my DUT and the test bench are working at the same edge, then that is a problem. Okay. Okay, so so this is my clocking block. This is how you write clocking and unclocking. Okay, and these are my signals inside your interface or module. Okay, and you can, so the idea here is to give the directions also of this particular signals A, B, C, D, and to specify the timing specs also. So when you write default input has 1 and output has 1, you are saying that you sample it. Input is my sampling stuff. You sample it just before 1 nanosecond to the passage of the clock, because this is what a default edge of sampling, a passage of a clock. Okay, and you are driving your output. Those which are output like signals would be driven at after 1 nanosecond, while the A, B, C, D would be sampled at 1 nanosecond prior to the passage of the clock. Okay, and you can also specify something like input negage of C. So rather than passage of the clock, you would sample at the negage of the clock. So all this kind of unique features you can take the advantage using this clocking block, which is obviously not present in the Verilog and in the SystemVerilog, so that to avoid any race issues between your design and the test bench. Okay, any questions here?
Yes, one question from Mr. Pankaj.
Sure.
He's asking, can you please pardon the concept of clock blocking? Clock
block means he wants me to understand again.
Yes.
Okay. So as I said, so clocking block is used to synchronize your RTL and DUT in a way. Okay, it is intended to make your driving and sampling easier. Okay, you can provide the input skew, that is the input skew and the output skew with the clocking block, so that you're driving from the test bench. So I'm driving here from the test bench, and I am sampling here from my test bench side. So as I mentioned, this is my test bench and this is my DUT. I cannot drive at the same edge at what this DUT is working, right? Because then I would have a race. DUT signal is toggling, and then even if I try to toggle from here, then there are high chances of race. Like you cannot interact what exactly it's going to happen, and you don't have any idea how my DUT is going to behave. And there will be obviously false design behavior within a DUT if you try to do that. So that's why there is an interface, and within an interface there are clocking blocks. Okay, and what clocking block is done here? You provide some setup and hold time, some buffer time before driving and sampling the signal. Okay, and this is the way you do it. You write a clocking block. I'm writing a clocking. I give any name. I'm sampling on a percentage of clock. Then I give an input skew, which I showed it. This is my input skew. I'm giving 1 so that it is not exactly at the same time. If I write input has 0, then it would be at the same point at this percentage. If I say input has 1, that is like clock minus 1. So it would be prior to this. And for output, if I write output has 1, it would be after this clock edge. Okay, so that is the beauty with which you can avoid a race of driving on the same clock. You just give to provide a setup and hold buffer. It depends on the design or specific. This is just an example point of view. If the design allows you to do that, you can change this value. Like if you do 2 year, then it would be 2 nanosecond before your passage of the clock. So say for example, my passage is coming at 5 nanosecond of a clock, then your input would be sampled at 3 nanosecond. And if your input is 2 year, has 2, if there is has 2 year, then your input would be sampled at 3 nanosecond, and your output would be driven at a 6 nanosecond. Okay, so that is what I'm saying. Your passage of the clock is coming at 5. If your input is 2, has 2, then it would be 3. Your inputs would be sampled at 3 nanosecond, and your output would be sampled at the 6 nanosecond. What are the input and output of the test bench, not of the DUT? Remember that. This is all on the test bench side. What I'm talking about. I'm not talking about anything on the duty side. Okay, because your clock would be generated from test bench, not within the DUT. DUT is just a design specific. It's just a coding. It's just a behavioral code of a functionality. It doesn't create anything, right? What is the new need of test bench? Providing the stimulus, providing the data, providing the real test scenarios, test vectors to the DUT. Okay. Did I answer your question, Mr. Pankaj?
Yes, sir.
Okay, thank you. Okay, there was another concept as I called was mode ports. Okay, so mode ports are used to specify the direction of signal that are to be used. So say for example, in this example, whatever the signals which I want to drive, from the test bench would be my output from the test bench and input to the DUT. But as of now, I'm just viewing from the test bench side. Whatever the signals I want to drive, say for example, there are clock I want to drive from the test bench. I want to drive the address data. Those would be my output from the test bench. So whatever the input at the DUT would be the output of the test bench, right? And whatever the output of the DUT, which are the signals coming from the output, would be the input to the test bench. So that is a major concept. We need to remember that, or we need to understand that to be specific. Whatever the input ports of the DUT, it will be an output port for the test bench, right? And whatever the output ports, output signals, output wires from the DUT, it would be an input to a test bench. Major concept of a test bench and DUT interaction. This has to be understood properly. Okay. And then, so while writing a mode port, so when I write a driver clock block, that is a driver I want to drive from test bench, all the outputs, that is what I want to drive, I would write as an output, because these are the signals which are output are now going to be from test bench. It would be an output, and what I want to sample and or what I want to get the value from the RTL, that would be an input in the monitor clocking block. So I have two clocking blocks here, driver clocking blocks and monitor clocking blocks. What are these address write enable? These are all the signals which is there inside the DUT, as well as so since it is inside the DUT, I would obviously have to write it inside the test bench, so that once I connect the DUT in my test bench, I can now drive it from the test bench and I can monitor in the test bench. Okay, and this is what I am giving a skew, input skew and output skew, which I just explained, and I am sampling at the passage clock. Okay. And with mode port, what I do is I write a mode port named as driver, and I give this entire clocking block, that is driver CB. and I say also input and my inputs and clock and reset are also input to the driver. Okay, so and for monitor I write this monitor clocking block. Now what this do, when you write clocking, all this would be an output for this one driver, and for all this that would be an input. So this is just a concept. If you don't understand that, that's okay, but these are just a concept, how easily you can create a test bench. Okay, so I am trying to cover as many as concepts which is there in SystemVerilog, and which is not part of the Verilog, in which you might not have even heard or listened about it. But these are very simple and easy concept, because if you get it, why this is output. So now anybody can explain why these are output and why these are input, like after what my explanation is, or I should still go ahead and explain again? If anybody has understood that.
Sir, as you had mentioned that the output of a test bench is input to the duty.
Correct.
That's why you had mentioned output for these ports and input for the other blocks.
Correct. Absolutely. Yes. And you can say that here the output and the input, both the signals are same, but it might not be same for the real test case scenario or real test bench or design signals. This is just an example that, okay, say for example in a design, these all signals are in out. Okay, in out ports. So this all signals can be an input and output as well. So if from test bench side, when I want to drive the values of this, I want to generate some value for address, I want to generate some values for enables, write enable, read enable, write data, read data. Those would be my output, and this would be my input, because now whatever the values is processed by RTL, I want to monitor that, I want to sample that, I want to know what is the values after I drive it, what are the values I am getting. Okay, so is RTL behaving as I expected or not? So with this, you can create a very simple interface, and this would be passed across the entire environment, entire test bench, across multiple components. So Verilog has only module and module. SystemVerilog has a lot of classes, and I can pass this interface across multiple classes. I'll show you that in my example of a test bench, how you can write a simple test bench of a memory design. I will show you the design as well, and I will show you how you can write the entire test bench also. And then in the hands-on section, if anybody wants to try, you can try generating the input and the output also. So that is also there. So this is a simple modport example I wanted to explain you. But even more than modport, clocking block is a very necessary step to understand what is clocking block and what is the exact use case of that. Okay. Okay. Any questions before I move to the other concepts of SV? I guess we would take a break once I'm done with the SV concepts. And I have another 4 to 5 slides only, if I remember correctly, for completing my SV concepts. Okay, I would go ahead. Okay, so SystemVerilog is another concept. This is just for your information. Mailbox, I would explain you when I go through the test bench writing, like, but mailbox behaves like a FIFOs, like first in, first out. Okay, you can send any data type. Say for example, I want to send integer from one class to another class. I can use this mailbox stuff. So that is how you can communicate between the various component using a mailbox in the SystemVerilog. Okay. Okay. So now in SystemVerilog, the major concept is another major concept is randomization. Okay. Now the OOPS concepts are done. Okay. Now and the SystemVerilog also, but I'm now going to focus more on what are the important thing which you can get using SystemVerilog, which is not there in the Verilog side. So you can do a constraint driven test generation, okay, which allows you to automatically generate multiple tests for functional verification. So this random testing is far more efficient than a traditional directed testing, which is done in Verilog. Like you are just specifying specific input. Rather than that, specifying random inputs would be very helpful, because that can create or find a new bugs which you might have not have thought of that. So by specifying constraint, one can easily create those tests, automatic tests, and find the corner cases. So why random stimulus is needed in a test bench? So say for example, you want to verify, you have written in simple Verilog code for this adder, and those are of 32 bits. You want to verify those 32-bit adder and check the output here. So simulation can check a result in 1 nanosecond, but say for example you want to exhaust all these values one by one. How much time it would take? Like it would take 2 power 32, 2 power 32, and those and then you divide all those combinations. It is impossible to completely verify a real design in a simulation when you give like 2 power 2 to 2 power 32 multiplication stuff. So you just constrain those. And how you constrain that in a system Verilog? Inside a class, you declare those variables as a rand, any variable like A and B you can say here, and then you constrain, give it the legal space. I guess in the last lecture, Usha ma'am was talking about giving a legal values and constraining it, your stimulus. So what I'm doing is in the system Verilog, there is a constraint keyword. You can give a constraint saying that okay, my P1, which is of 2-bit, so it can generate a value either a 0 0 0 1 1 0 or 1 1. You are saying that please don't generate a value 0 0 because I know I don't want it. My design doesn't allow me to do that. Okay, and then there is a keyword called as randomize. Okay, what you are randomizing? This particular class object. Okay, as if in the earlier system Verilog concepts, what we saw was you can do a new, you can extend it, you can inheritance. There is another thing also, that is you can constrain the random variables which are declared as rand or randc, and you can declare this is my class object which is you are doing new, and you can randomize your entire class using this dot randomize method. So whatever the rand variables are here would be randomized, okay, automatically. The tool will do it. You need to do it. Just write this line and tool will generate this. Okay.
Sir, I think
Yes.
your slides are stuck at mode pots.
Oh, is it? Oh, sorry. Let me share it again.
Yes, yes, Sagar.
Oh, I didn't know that. Thank you. Is my screen visible now or still not?
Yes, yes.
Are you seeing the randomization?
No, we are seeing your screen.
Like it has the
MS
randomization slide?
No, MS Team screen. You go to sharing your slide.
Oh, okay. Oh, I got it. Is it visible now? Let me know.
Yes, yes, yes.
Okay, perfect. Okay, so sorry. I'm sorry. Thank you for telling me that. So what I was explaining was this example. A and B are the 32-bit input to get an output of C, which is all the inputs are of 32-bit space. So if you want to generate all the legal combinations, what I was mentioning is you have to give 2 power 32 into 2 power 32 combination of this two, and it would take a long time, mostly impossible to verify each and every value and see the output of that. So that is why giving a constraint, randomizing it, and then giving a constraint and making your space a legal one is more important. So in a system Verilog, you have rand variables. You can declare any variable. So here for this particular example, declare A and B as a rand. Say you have A and B, and you can constrain it. Now for this example, what I'm showing here, I will make P1 and P2, and both are rand variables. This is of 2-bit P1, like so it has a value, it can have a value 0 0 0 1 1 0 or 1 1, 2 power 2 combination possible. I'm saying that I'm writing a constraint. This is the C1 is any name what you can give. P1 is this variable, and I'm saying that not equal to 2 comma B00. So what does that do is it will never generate a 0 0 value when randomizing this P1 variable. So you are ultimately saying that only generate 0 1 1 0 or 1 1 value. Okay, and with this way, oops. by doing a dot randomize on this class, so I'm taking an object my rand of this class, and when you do a dot randomize, with this way you can say that okay, you are constraining that, and your values would only be generated or only would be limited to 0 1 1 0 and 1 1, and it would never be generated to 0 0. So that is the important reason why you want to give constraint and why you want to randomize. Okay, because randomize is allowed only if you write a rand bits here or rand variables here, and the constraints are allowed only on the rand variables. If you remove this rand and if you have only bit inside a class, you cannot write a constraint on that. Okay, is that clear? Okay, so that is why random stimulus with SV is very important. Okay, now I did talk about the coverage in one of the slide, like SystemVerilog allows you to have the coverage. So there are two types of coverage analysis, which most of you might know: code coverage and functional coverage. So code coverage or expression, statement, branch, toggle are automatically inferred by simulator tools which you are using. For writing a functional coverage, you need to do it something different. You need to know what kind of functionality you need to attend. Say, for example, in FIFO, take an example of FIFO, you check what would be the functional scenarios. FIFO full, FIFO empty, okay? Those kind of functional scenarios you want to check. So you might need to write specific functional coverages for that, whether you have covered all those cases or not. Okay, you have written the test case, but whether you have covered or not, you want to still check it. So normally, the objective is to reach 100% for code as well as functional coverage in the industry also, so that I can say that okay, my complete verification is done. So for every functionality in the industry, they write some cover points or cover group, I can say. So say for example, this is my bit B. I want to check it whether I have covered all the functionality like 0 0 0 1 1 0 1 1 or not. Okay, so for that I write a cover point B. Okay, inside a cover group. So this is how you write a functional coverage in SystemVerilog. You need to again instantiate that using new, similar to like what you do for a class. So that is why I explained all the OP concept, because SystemVerilog take advantage of that in multiple ways. Okay, so this variable is sampled on every negate of the clock. Okay, is sampled on every negate of the clock, and 4 bins are created okay, automatically by the tool. It would be created because it is a 2-bit type, 0 0 0 1 1 0 and 1 1. Now for example, if you run simulation 100 times, okay, we can get, I'm just giving an example, we can get result in this form, like b was 0 0 for 50 times, b can be 0 1 for 20 times, 1 0 for 20 times, or 1 1 for 10 times. If say for example, if somehow your stimulus was not 0 1, like you constrain that okay, it should not be 0 1, then we have a coverage whole of 75% coverage only. Okay, so that is why it is very important to write this kind of cover groups. So for FIFO empty, FIFO full, you can write such kind of cover groups or functionality. Or for in memory case, you can write something like write, read, enable, whether they are covered or not, or memory is my full or not. You can write all those kind of scenarios using this cover group and check it out. So generally in industry standard, we do have a lot of cover groups and cover points, but this is just a basic which I wanted to give an idea. So instead of tool creating the bins, you can create your own bins in using that. So I have a variable VA, and I want to create a bins for that. Okay, so these are the names of bins. You can give any other names. So I'm saying that bin A should be 0 to 63 or 65. I can create 3 bins like this. I can create a bin like this, or I can create some 7 bins like this. So there are ways to create the bins within this 2 power 9 VA combination. So this is just an example I wanted to show, and this is how it is done in the industry. Yes, any questions? Why 7 bins? I was looking for these questions, like why 7 bins? So it would be 10, 11, 12, 13, 14. That are 5, and 16, 17, 18. Like so, 4 plus 5, some 7 bins would be created, and it is an array, so that's why 7 bins. If it would be a C, is like simple. So only 1 bin is created for the entire stuff. Even for this, only 1 bin is created. So any value, what does mean by array of bins or a single bin, a scalar bin or a vector bin? Say for example, any value of B is generated from 0 to 63 or 65. this bin would be covered. So if all my 5 bins are covered, then the coverage goal for this is 100% achieved. That's it. Okay, and this is these bins are written not automatic, like not without any understanding. You need to understand the spec and then write those bins. Okay. Any questions? I guess we can take a break, sir, like for 5 minutes if people want to, or whatever you say. I'm fine with anything.
Let continue. We have break after your session.
Sure. Okay. No, I guess maybe it might be difficult for some people to understand. So that's why I thought of. Okay, I'm fine. Okay. So now I'm done with the most of the concepts. I'll just start with the example of the test bench and what is test bench exactly. Okay, so if nobody knows what is test bench, as I had explained, it is used for verifying your DUT. So the test bench components are written in Verilog SVU to verify the test bench. Usually a test bench contains the following functionality. Okay, you have your interfaces, your driver, clock, reset, and other control signals. It controls your test duration. So as you say, I create a test bench, I instantiate the design in the test bench. Okay, your design would be within the test bench. You provide your stimulus, that is you constraint, you random, you provide the stimulus, compile the design, test bench design in the simulator, run the simulator, observe the outputs. Okay, and verify that whether the logic of the design is as intended or not. Okay, so this is what a simple test bench workflow looks like. Okay, so now I'm going to give an example of SV test bench for you. So what does top would have in an SV? I'm just giving you to make you understand the different components used by the test bench. So generally, this is my duty. I am going to show you now the example of memory duty. I have a memory duty. Let me show you first that so that people know this kind of coding first. I'm doing a parameterized memory module stuff. I'm passing address, data. I have an input, clock, reset, address, write, read enables, and data also, and I have an output, read data. Now, this is a simple logic of memory, and this is your simple design of your memory. Now, to verify this in Verilog, you can write various modules, various test case in the modules, but with SV, the story is different. You have to write top level, which is your module, like which is your static part. In that, you will have a lot of components of the test bench, which I'm going to show, like stimulus, generator, driver, monitor, scoreboard, and from I'm going to explain you each functionality of each and every component. So this is what kind of a structure of a test bench look like. So test bench contains a top, as I have explained here. Within top, a test bench top, it contains the instance of the DUT, a clock generator, like you generate a toggle a clock, and others. And if you have, this is not a mandatory, I'm just giving an example. Within the top also, you would have a test case instance, and a test case would have an environment instance. An environment would have a driver, monitor, scoreboard instance, all of that. So see the beauty of class. Since you are using a class-based test bench, I can have a hierarchy of the different stuff. Because object A dot, object B dot, object C dot, like a test case dot, environment dot, a driver dot, I can go to any of these methods, right? Because I want to access to any of these methods. So from test case, you can go down to the deep of any signals in the and can access it. Like from test bench, you can control the entire. From test case, writing a simple test case in SV, you can control a lot of stuff within the test bench. So that is a beauty of writing a test bench in SV, which is not present in the Verilog, and that is what I said when I was giving an example of a new mobile. Say for example, one operates on 64 and one operates on 128. If I change anything from the test case, it would go and change within your entire environment in the test bench. So writing in that way, I'm going to give an example, don't worry. So, but these are the various components which would be part of environment, and from env handle class, and all of this would be in class based. Okay, nothing would be in module based. All this would be class based. So when you write env dot driver dot or give some value here in the stimulus, which is might be a driver, or in drive method, you can control it from test case. So that is the beauty of writing a test bench in SV. Okay, and as I explained, I'm going to explain you regarding this duty. So this is my RTL signal written in Verilog. So what would be my test bench architecture? As I explained, there would be an interface from your duty, and this is my entire test bench. You have a top, and inside test bench top, you have an environment. I have not shown the test case, but it would be a part of that. There would be a generator which generates the value. VFM is nothing but your driver component, which drives the value to the memory. And then when it comes back via interface, it goes to the monitor, which you can pass to the reference model. Reference model is nothing like you want to compare the values, like whatever you have generated is coming back or it is processed by the RTL. You write a scoreboard on that. And also you can write a coverage model, which I showed just now, like cover groups and cover points and bins, all of that. But my main focus is for the today's case would be in the example would be top, environment, generator, BFM, interface, and then monitor. Okay, I'm not going to show the coverage in the reference model, but this is how you can write your test bench. So as I explained, you instantiate this memory duty is within top, as you have seen. Like this is my entire top. You can see here, and this duty is within that. Even interface is within this test bench top. Okay, so I'm going to instance my interface within top. I'm going to instance my duty within top. Okay, and I'm going to instantiate my test case, which is there about this environment. So test case would have environment, and environment would have generator handle, VFM handle. Then via VFM, since this is connected, you can access to the interface to the memory duty. From memory, it processes everything. It comes back the signals. It passes the signal back to the interface and comes back to the monitor and then goes back. So this is the entire flow of your test bench. If you understand this, I guess my main motive would be fulfilled for today's lecture. So this is a basic idea of the entire test bench in the SV, and it is all class based. So that is why I was explaining you all the class concepts so that you can understand. Any questions here? Because now everything would be a core.
Sir?
Yes.
Sir, you had shown this test bench architecture. So this is common for all the programs, or this will be changed?
This will be changed. So this is just a environment. This would be changed in UM. Say for example, there are like multiple interfaces. Like this is only one interface. Now you have an SoC, a system on chip. Okay, where you have a USB interface, PCI interface, DDR interface, AMBA XIHB bus interface, UART interface, I2C interface. Then you might need to have a different environment for each of those interfaces also. I'm just giving you an example. So in an huge SoC, there will be multiple environments similar to this. The components would be same. So all the environments would have mostly a generator, a BFM, a monitor, but there can be multiple environment in an entire SoC chip, or it can be a single one. So generally it goes like there will be small environments and there will be a top environment in an SoC. I'm giving the SoC real industrial experiences. You have 10 environments, small environments for each interfaces like PCIe, USB, GPU, SPI, UART, and then there will be all those environment will be instantiated or would have an handle in the top environment. Okay, so entire data from the top comes and it then splits into the 10 different environments, and then it goes to this level. So that is how it is done.
And so, sir, for all environment, we had to write the generator part, the coverage part.
Yes, it depends on the design also. Like coverage, sometimes it's not required, sometimes it is required. But obviously, if you want to drive anything, you require a generator BFM. If you just want to monitor something, you need not need to write BFM or generator. Just monitor this interface. You want to have a component which you want to write just monitor, then you can have only monitor also. So you can pick and choose any of that.
And sir, last question, sir, as you had shown that arrow from generator to BFM is only a single direction.
Yes.
While from the environment to memory duty is bidirectional. So sir, so the generator and BFM, they can't communicate with each other.
Correct. That's
sir,
what absolutely. Yes, absolutely, you are right. Because you are generating the data and you are sending the testbed to drive it to DUT. This is my class. Okay, this is my class. I'm generating the data, and so there can be a way where you can back channel it. Like you can declare, you can take a use of mailbox which I had shown you. Like you can communicate. There can be a way, but generally that is not done in the simplest of way, because you have to communicate or connect them. But it can be done. But for this particular example, what I'm going to show for this particular test bench, it is only one way. But there you can do it in the real model. You can do it like you can do bidirectional also. Okay. But for my example, I'm going to be I'll just mention like what I'm doing. Yeah.
Okay, sir. Thank you, sir.
Yeah, very good question. Any other questions? Okay, so then let me start with the interface. Okay, I'm going to first start with the interface from the testbench side. So interface has all those signals which are there here. I was just showing here in there also. So it has all these declaring signals which I have just done the logic, and then I have written the clocking blocks which I had shown you earlier and the mode codes. So your interface is done. You have written the interface now. Okay, and you are passing clock and reset from the external world. Now you want to write a top. Okay, so what is top? This is top I am writing now. Okay, oops. Yeah, so this is top. Top has clock reset. You are generating the clock here. So this is your clock generator. Okay, you are generating the reset also. So this is your reset generation. Now in the previous slide I had mentioned top has the instance of interface which you have already written in separate file, a DUT which you already have written in the separate file, and a test case. So when you see the this one, this is my memory interface. So memory interface, name of the memory interface, INTF is the instance, and you are passing clock results. Know that this is a static stuff. It is not a class, so you need not need to do a new of the interface. It is similar to module, so just instantiating like module should be fine. Like what you are instantiating. See, this is my dot. Memory is my dot. Okay, my memory module, and I'm just giving a name dot as an instance name, and I am passing the interface signal which is there inside the test, which are there inside the interface, from interface.clock to this clock, interface.reset to this reset, okay, to here. You got it? So this is how my connecting interface to the DUT. So this is how my test bench is connected to the DUT. Is this clear? Because this is very, very important. Anyone can say that it is clear to them?
Yes, sir.
Or any question? Yeah, great. Any questions? If you have questions, please, because this is a very simple thing, but you need to understand the concepts. So in top, believe me, in any environment, you would have an interface instance and a memory instance, a DUT instantiated, RTL instantiated, and your test case instantiated in an SV test bench. UM have something different, but I'm not going to talk about UM today, because that would be require me another 3-4 hours of speaking. Okay, so this is my test case instantiated. I'm going to show the test case in another slide. What is this test? It is a program block written, and I'm going to show that in another slide. But what I wanted to show you here is the interface and the DUT are being instantiated here because they are always part of the top and they will be instantiated in the top. Now, if you are a very good learner, from understanding the diagram, you would figure out now environment would have the instance of generator, BFM, coverage, blah, 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 or monitor. You would create everything inside environment. Since I have created my test, my interface and my memory inside my top, seeing the diagram, this is how you can do it. So when as a if you once you know the SP, and when in an industry what they would do is they have these diagrams with them. So that's why I have given this diagram. When we write a test bench, we have a diagram in front, and from knowing this diagram we write our codes. Okay, so first this diagram architecture is created. You have a plan, you have the duty, you create the architecture, and then you write the codes. You cannot just by gun jumping write the code straight away. You first create this architecture before writing any test bench code in SP or EVM. Okay, so this is the starting point of the entire test bench. Okay, and now I'm going to show the test. Like, what is this test? So it is a program block similar to what your module end module is. Inside this, you can write a class. I will show in the so Coringa sir will show in that in the demo. It is there in the demo. You can see that. I'm not shown here, but inside this test, I'm creating the env as I had said, and inside env there would be an instance of generator driver, and I'm having so inside the generator I'm having a repeat count which I'm accessing from env, and then I'm calling a run. This is, I will show you what is this all stuff, but I'm just showing like what does test contains. The other advantage of this test is it is passing the interface. So everything, once interface is instantiated, INTF is instantiated, I can pass it everywhere, like to my a test case, to my DUT, to connection. So from here, my interface is passed to all the test bench. So I'm passing now to the test, and test will pass it to the, this INTF will be passed to the env. Okay, I'll show what env is. Okay, so now let's see the env. I know the font size might be small, but yeah, but let me know if it's very small. I'll try to capture it, but I am sure you might be able to see that. So this is my class environment. Yes, any questions or any comments?
No, participant can enlarge that zoom their screen. No.
Okay, perfect. Thank you, sir. Thank you. So this environment class is this one. So I declared that environment handle here in the test, and I've created that environment in the program block or the test. This is my test case, actual test case. Okay, so inside environment, I'm taking generator, driver, monitor, which I had shown you here. Again, I'm going back here. Generator, this is my BFM is driver, and my monitor is monitor. Okay, so I am taking all that instances here. I am taking instances there, and I am creating here. Here you can see creating generator, driver, monitor. Okay, now there are mailbox also I have taken, which are important concepts. Mailbox one has there are two mailbox in this. One is I am sending the data from generator to driver, as somebody has asked me, and the other is monitor to scoreboard. Obviously scoreboard I have not seen here, but anybody who is willing to learn SP, you can try in the demo which I am showing. And there are the tasks which I have written, like pre-test, test, post-test. Inside the run, all these three tasks are called like pre-test, test, post. So this run, I called it here. Okay, I called this run in the test case itself, so that a pre-test has drive your reset. A test has like you generate the you generate the stimulus and then you drive. Okay, and post test is like when the my generation is done, you just wait for the number of transactions to be done. So all these three tasks would be completed here. And see the use of fork join any again. So that's why I explained you the fork join concepts. Anyone is finished, this task can get finished and I can proceed to the post test, something like that. So that's what the main use point was saying. Even mailbox, you can see here gen to drive, monitor to scoreboard, gen to drive, monitor to scoreboard. You are creating the mailbox. So mailbox also needs to be do new, like similar to what you do for class gen to here. And for generator, driver, and monitor, you are passing for the mailbox as well as the interface. But driver and monitor requires the interface. The generator doesn't require the interface because generator is just generating the stimulus, nothing else. While driver and monitor will drive to the interface or will sample from the interface, as you have seen in this diagram. Here, your interface is only connected to your driver and monitor. So if you now understand the concept properly, I'm passing my VIF, which is the virtual. One more thing which I forgot was to within a class, if you want to pass a any interface, you have to declare it as a virtual, because class are dynamic while interface are static. So to make it a dynamic, you just need to make a virtual. So virtual is nothing but a pointer to make it a dynamic. Okay, you cannot pass mem interface, mem VIF handle. To make it, need to declare a virtual. While here, inside this, you without virtual also you are able to pass it, because this is a module and this is a static. This is a static stuff. Okay, once it is created, it would be there. Their memory would be lifetime. While class can be created, their memory can be allocated, deallocated, deleted also. While this, so just keep in mind that fact. I don't want to go in detail and mess your stuff, but this is what you need to create a virtual interface so that you can pass it to the different components. You pass it in the new constructor only, like where you are creating within all your components like generator, driver, monitor. You pass it here from mem. So from test, you can pass it to this guy, env guy. From env, you are passing it to driver, your monitor. Okay, so that's why here you are seeing in the new, I'll be having two arguments. Here I have only one argument of the env new. So that's why you can see in the env when I'm doing new and tf, there is one argument pass, which is declared here, which would be passed to here. Okay, so from program log, whatever the interface, and this interface came from here, like from the top. So from top it came to test case, it came, it passed to env, and from env now it is passed to your driver and generator, right? Because as you see in the diagram, the top has the interface, right? There is no way, and the env has the bfm. So how you pass the interface to BFM directly? No. So from top only, you have to pass it. You pass it to the test case. It comes to environment, and environment passes to BFM. So that's how you pass the interface handle to your BFM. Okay. Did any questions here? Okay. I guess it might be too much for a lot of people, but it is very simple once you understand the code and try to figure it out what exactly it's going. Okay, what are mailbox? As I said, I want to send some data from generator to driver, so that's why I'm using the mailbox. I want to put something. I have created my transaction now, packet class, say for example, and I want to drive it from the driver to DUT. Okay, so that's where generator comes into the picture. Okay, so what does generator and transaction class does? Generator is nothing but it randomizes the transaction class entirely. Okay, and so this is, as you see here, this is I'm doing a randomize of a transaction class. So what is my transaction class? This is my transaction class. I have a lot of rand variables as I had shown you, and I have written some constraints, and I have done the post randomize. So when you do a dot randomize, it does do pre-randomize, randomize, and post randomize. It does 3 steps. So this is a part of the post randomize. So automatically when you do dot randomize on this class, that is here, dot randomize, those statements would be printed. Okay. So now from env, when when the Jane dot main task would come, it would come here, Jane dot main, because all this is done in the function new. Your transaction is being ran. Your mailbox, you have got the mailbox from the environment. You do a main, and it would come and it would do this. It would create the transaction class, and it would do a randomize that. And then this is my mailbox, Gen to drive. It would put that randomized data to in the mailbox. That is a put. Okay. This is a important statement here. I am putting my transaction class which I have generated and randomized to a driver. So now I am driving a randomized value, not the hard coded value. Okay. So when you go to the driver, the first statement here would be get. You are getting that transaction here, okay, which you have put in here, you are getting that in the driver of the main task of the driver. You can see here. And now what you are seeing here is I'm from the transaction class, I'm driving to my interface. So this is drive if is nothing but memvif driver dot clocking block. So how this is converted, let me take you back. So here, if you see here, driver clocking block, driver, so there is a mode port driver, and inside that there will be driver clocking block. And this is my memory interface. So interface dot driver clocking block. So everything is hierarchical in SV, as I had mentioned. So this is my macro I have defined. Okay, so with this, you are now driving to the actual interface. Okay, so everything is now being driven to the actual interface using clocking blocks and mode ports. Okay, so the first statement, the thing to be identified, noted here is to get that particular transaction and then to drive that on the interface. Now this is my logic, and I am running in the forever block. Like it is continuously running because you don't know for how many times you would be bombarded. So as many as transaction you can generate 100, 1000, lakhs. How many transactions you want to generate, this driver would keep on running. Okay. So this is how the entire flow is being generated. So you first generate the data and then you generate from the generator, you put it on the driver using .put method, and you using .get method, you get it here in the driver. So this is how you can transfer the flow from one component to another component. Okay. So even if you have not understand, let me just give you. So here it would have .put method, so that it is implicit. Mailbox is an implicit .put method. You declared a mailbox in the environment. You created that. You passed it here. Now you are putting the data in the mailbox. You are just transferring the data to the driver, and driver will convert those data from TRNS to your interface through here. So this is how flow. Because this is same, you just need to put and get and put here, and now this guy has to convert that generated data into the interface data. So that is why that code is there in the driver. This code is there. Like see, if you see trans.address, so the generated address is being now driven to the interface pin vehicle, like exact pin on the pin you are driving. Okay, using this write enable, you are driving in the pin. Same for W data, same for read enable. Similarly, something for all the data you are writing and reading on the exact pins of the DUT. So that is what a beauty of SV test bench is. You have the flow from the top and you can control it to the bottom. Okay, and similarly, when you see here at the monitor, for the monitor, what you can see is you have the data monitored from the interface. Okay, and you are from the interface you are monitoring it and converting it to the transaction packet. You have taken the transaction packet, even this is running forever. Okay, so from every interface, so here if you see the difference between driver and monitor, the interface is on left hand side for the driver, while right hand side is your transaction packet. You are driving with non-blocking statement, and on the monitor side, class monitor, you are reading the interface value, that is the interface values which is coming from the DUT are on the right hand side, and you are now converting into a transaction packet. Why we are doing this? Because I want to compare in the scoreboard, so that once I have this packet, entire packet ready, I just put it again using the mailbox, using .put method, send the data to scoreboard. Any questions? If you can mute it, yeah. Thank you. Okay, so that is it for the SV test bench. Any questions? I'm just going to now quickly explain you about the UVM stuff and the trends. SV side is over. So this is how you write a test bench from now. If you, after understanding the code also, if you understand this architecture, it would be very simple. When you see the code, just look at this architecture and how it is done. Then you would easily get to know it. Was that useful for or no? So this is an example. Believe me, this is how we code in the industry. This is all real examples which we code in the industry. Any questions? Okay. Let me go to the UM. So as you would understand that there was a within an environment in UM there was a generator, driver, and monitor. It is going to be same in the similar in the way in the for the UM also, but in the UM there are multiple agents. So say for example, I want to write and then I want to read. So you can have a write agent and a read agent. So your generator will be requested by a sequencer or a sequencer, and your driver monitor would be same. I have now two agents because I can interact with the same interface in different ways. Like there can be a separate agent for a write or a read. Or give a specific example, I can have a master agent if any, or in a slave agent. Okay, for SPI, I can have a MISO agent, I can have a MOSI agent. So something like that, if people understand, this is just a basic diagram of UM. I don't want to go in detail. Others, all components would be same, which is part of the SV, but this is just a one layer or one layer above the UM. So why UM is so much popular now, and what is UM? So UM is obviously a methodology based on a SystemVerilog. Is not a language on its own. Okay, it's just based on SV. We are extending a lot of stuff from SystemVerilog. It is a standardized methodology, so it has its own class, own libraries. Okay, so with that you can reuse it, and it is also part of the IEEE. Okay, so UM is a base class library. If you see, it has its own class library. If you can mute it, that would be great. I'm sorry. I'm hearing a lot of background noise. Thank you. So UM is nothing but a base class library which helps you to use certain features of UM not possible through SV. So it has specific class like so UM driver, UM monitor, UM underscore monitor. So those are libraries created for the reuse. Like so that's where you can take the advantage of reusability using the UM. So and obviously it also has the sequencer methodology which gives good control on stimulus generation. There are various ways in which sequence can be developed, which includes randomized layered sequence, virtual sequence, etc., which provide good and rich stimulus capability. Obviously I'm not going to go in detail because I know uh, I've given you too much to digest, but this is just an overview. If you want to look into that or if you have any doubts, you can obviously contact me for that anytime in the future. So maybe this slide might be more and more useful for some of them. So what is the future of design and verification for? If there are any engineerings or like any professors who think that why this is important, there are currently there are huge scopes when huge chips going in this AI, ML, IoT, automatic chips, mobile phones, memory, 5Gs, data storage. So there is a huge career opportunities. I guess somebody had asked me in this lecture only, like, is there a myth of like what are the packages and all that stuff? Forget about the money. It is on par with the what you get for the software in Google, Amazon, Facebook. Uh, there are a lot of severe lack of talent in the industry. We feel right now we need skilled engineers always as designs are getting more and more complex. There is huge SOCs, so there is huge such things which we need to develop and verify, design and verify. Earlier, 20 years back, only people from IIT, NITs were incubated by the companies because this requires specific skills. But now that has been changed. Me being part of the government college, Rajkot, I have made through, and there are a lot of people like me who have now made through in VLSI industry. So that mindset needs to be changed. There are still a lot of people who comes from IIT and NIT directly to this domain in design and verification domains, and they work with people like us. So that again is a myth which we need to be take away from. And more companies are now trying to make their own chips, like Facebook, Amazon, Reliance, Google, Microsoft. So obviously they would pay according to the industry standards. So this is the career is huge, the path is huge, the opportunities are huge. We just need good engineers from the industry side. That's what I can give you the message. So the references for this presentations were from Verification Academy and Test Bench. You can also note my email ID and my LinkedIn ID. You can contact me anytime for any queries or any questions you have while you refer a SystemVerilog or you. So that is it from my end. Thank you.
Yes, if you have any questions from the participant. During the session, many questions has been already asked and solved by the Sagar. Yes, if you have any more questions, you can ask. Okay. So I think, Sagar, no more questions from the participant. So again, thank you very much, Sagar. You have spared your precious time for us, and you have presented very nicely the class, starting from the class-based concept to SystemVerilog, and that also highlighted the features of in a verification domain. Thank you, Sagar, behalf of Government Engineering College, Rajkot.
Thank you, sir. Thank you again for giving me the opportunity. Thank you.